W by Ws, actual humidity ratio divided by saturation humidity ratio. But we know from the first relation W is equal to 0.622 into PV by PB minus PV. Similarly, putting for Ws under saturation condition, of air, Ws is equal to 0.622 into Ps by Pb minus Ps. Please note that Ps is the partial pressure of water vapor at saturation condition. Therefore, mu is equal to, substituting for W and Ws, Ps by Pb minus Ps. So it results in Pv by Ps into Pb minus Ps by Pb minus Pv. But Pv by Ps is 5. This, since Pv is lesser than Ps is lesser than Pb, but this bracket Pb minus Ps divided by Pb minus Pv is almost equal to 1, implies mu is equal to 1 but less than 1. Mu is almost equal to 5 but less than 5. If say phi is 40%, mu will be around 0.39 or so, the degree of saturation. Now let us discuss about psychrometric processes. Very important topic of air conditioning. Let us see the various psychrometric processes which are very important in the gate point of view. The first process is sensible cooling. It is the process in which the dry bulb temperature of moist air is decreased by passing the air over a cooling coil without change in its humidity ratio or specific humidity. Indicating the process pictorially, if this is the cooling coil, the moist air is passed over the cooling coil, hot moist air, it is leaving in the colder moist air, but W is not changed. That means we are not removing any water vapor or humidity from the moist air. That is, the temperature of the moist air is not brought down to the dew point temperature of the moist air. So representing the process on the psychrometric chart, the process goes like this. This is state 1, this is state 2, this is dBT, this is W, in this process specific humidity is not changing, but dBT is getting reduced. The effects in this we can watch that. Number 1, dBT decreases. Number 2, specific humidity remains constant. Number 3, RH5 increases. We can see that this is phi1, this is phi2. Phi2 is more than phi1 because state 2 is nearer to the saturation curve of 100% phi. Number 3, dPT remains constant. Number 4, this is number 5. Fifth effect is wet bulb temperature decreases. So we can see this is WBT1, this is WBT2. So as we have seen from the figure, WBT1 is more than WBT2. Wet bulb temperature decreases. Enthalpy of the moist air also decreases. 7th, the specific volume of air decreases because that as the temperature of the moist air is decreasing, its density will increase. Increase in density means decrease in specific volume. Here it is important to note that in the psychrometric chart, constant enthalpy lines run parallel to constant WBT lines. That means if enthalpy of the moist air is constant, implies wet bulb temperature of moist air also constant. This is an important note regarding psychrometric chart. Here now let me define bypass factor of cooling coil. If we take the cooling coil, the moist air is entering at state 1, whose temperature is TDB1. It is leaving at TDB2. Let the surface temperature of the cooling coil be T3. Let T1 is equal to temperature of moist air going into coil, and T2 is equal to temperature of air leaving coil, and T3 is surface temperature of cooling coil. It is not theoretically possible for each molecule of moist air comes into contact with coil. Hence, T2 would definitely be more than T3. T2 would be equal to T3 only each and every molecule of the moist air passing over the coil comes into contact with it and transfers its heat to the cooling coil. That is only a theoretical assumption. Practically speaking, there is always some bypass of air. What is bypass air? The air which is not coming into contact with the coil but passing over it. So T2 would always be greater than T3 practically. Therefore, bypass factor of cooling coil X is equal to T2 minus T3 divided by T1 minus T3. It is approximately 0.1 to 0.2. That means 10 to 20% or 15% of moist air would not come into contact with coil but passes over it. So 15% air would have gone bypassed over the cooling coil. Then efficiency of the coil is defined as 1 minus bypass factor. Now coming to the second psychrometric process, that is sensible heating. It is the process in which the moist air gets heated up while receiving heat from the heating coil as it passes over it. Without change in humidity or water vapor content. If this is a heating coil, cold moist air enters the heating coil. This is hot air leaves the coil. It is just similar to our room heater. In these peak winter seasons, we will be keeping a room heater, which is nothing but an electric coil supplied with electric current, getting heated up and transferring its heat to the surrounding air by natural convection. So that is just similar to this psychrometric process. The process could be represented on a psychrometric chart as phi1, this is phi2. dBT increases, specific humidity remains constant, enthalpy increases, etc. The effects of sensible heating process could be seen like this. Number 1, dBt of moist air increases. Number 2, relative humidity phi decreases. Number 3, specific humidity W remains constant. No change in water vapor content of the moist air in this process. So W remains constant. Fourth, dPt, dew point temperature, also constant in this process. Number 5, WBT increases. Number 6, enthalpy of the moist air also increases. Number 7, specific volume of moist air increases. Because temperature is increasing, density of the moist air will decrease. Decrease in density indicates increase in specific volume. If we look at the bypass factor of heating coil, if this is a heating coil, how that heating of the coil is done? By passing steam into the coil or electric current. You can choose any method, but coil must be hot to transfer heat to the cold moist air at temperature of T1 degrees centigrade. This is hot air leaving the coil at T2 degrees centigrade. T3 is the surface temperature of coil, heating coil. Then bypass factor of heating coil X is T3 minus T2 divided by T3 minus T1. That means if each and every molecule of the cold air had passed over the heating coil, the temperature of the air at the exit leaving the coil would have been equal to the surface temperature of the coil. But it is not theoretically possible to pass every element of the air to go contacting the coil. Therefore, the leaving temperature of air in this case would definitely be lesser than surface temperature of the coil. This bypass factor is in the range of 0.15. Here also efficiency of the coil is 1 minus bypass factor of the coil. Here I want to give note that if X is the bypass factor of each coil, then overall bypass factor of n coils arranged one after another as shown in figure is let there be any number of coils, n number of coils. If X is the bypass factor of each coil, then overall bypass factor of all the coils put together is equal to X to the power of N, where N is the number of coils. Now coming to the third psychrometric process, that is cooling with the dehumidification. Dehumidification means removal of water vapor or moisture from the air. In this process, in this psychrometric process, the moist air is passed over a dehumidifying coil whose temperature is lesser than the dew point temperature of ingoing air. If you want to remove the water vapor or moisture from the atmospheric air, from the moist air, it is necessary to make the water vapor condense, for which the temperature of the moist air must be brought down to dew point temperature or less than it, because only when the temperature of the moist air reaches dew point temperature, there would be condensation of the water vapor or moisture. So, to remove the water vapor, it should be condensed, for which the temperature of the moist air must be brought down to dew point temperature or even less than that. In this process, same thing is done. If you look at the coil, which is a AC coil, air conditioning coil or dehumidifying coil, to maintain so low temperature of the coil, we have to pass refrigerant liquid in. This is so the coil corresponds to the evaporator coil of a refrigeration system. So the refrigerant leaves in the vapor state. The latent heat required for this change of phase is taken from the moist air. So hot and humid moist air is entering the AC coil or dehumidifying coil. Cold and relatively drier air leaves. So definitely there is some collection of liquid, that is water vapor, that has been condensed. Little liquid is collected at the base of the coil, because when the hot and moist air is passed over this AC coil, some water vapor gets condensed and drops. The process could be indicated on the psychrometric chart like this. This is dBT, this is specific humidity or humidity ratio. The process is indicated like this. 1 to 2 is the cooling with the dehumidification process. So in this process, both the temperature and specific humidity of the moist air are getting reduced. So the effects of the process, if you look at, number 1, dry bulb temperature decreases. Number 2, specific humidity or humidity ratio decreases. Number 3, wet bulb temperature decreases. Number 4, enthalpy of the moist air decreases. Number 5, RH5 increases as shown in the figure. It may be even remain constant also. But in this figure, phi1 is away from the saturation curve. 0.1 is away from the saturation curve. 0.2 is closer to the saturation curve. Therefore, phi2 is more than phi1 in this figure. Sometimes it may be even constant also. 6th, dPT decreases. 7, specific volume of moist air decreases. These are the effects of the cooling and dehumidification process. In fact, this process is used in the summer air conditioning. In the summer, the atmospheric air temperature is hot and also it has more humidity content. When this air, atmospheric air, is passed over the AC cooling coil or dehumidifying coil, the temperature and humidity content are reduced, and this relatively colder and drier air is allowed to pass into the room where occupants are there, and this colder and relatively drier air would be able to pick up the heat from the occupants or the things present in the room, thereby making them feel comfortable. That is what we see in the summer air conditioning systems, where atmospheric air is very hot. In all the above cases, the capacity of coil, whether cooling coil or dehumidifying coil, can be taken as m dot of air, in this case in the dehumidifying coil, in the cooling with the dehumidification process, into delta H of moist air. In this case, mass flow rate of the air into H1 minus H2. If this is in kg per second, kg of dry air, and enthalpy being given in kilojoules per kg of dry air, so the resultant unit will be kilojoule per second or kilowatts. This is the formula for capacity of the cooling and dehumidifying coil. Next process what I consider is heating with the humidification. Humidification means adding the water vapor or moisture to atmospheric air. In this process, first of all, air is passed over a heating coil. Cold and relatively drier air is passed over a heating coil. The hot air, into that hot air, I spray the water. So water is water sprayers they are. So why it is heated first? The high temperature air always have got the more capacity of the keeping the water vapor with it along with, as compared to the low temperature air. High temperature air has got more ability or capacity of holding the water vapor along with it as compared to the low temperature air. Hence, when the moist air is first heated up, it could easily pick up and store the water vapor along with it. So the result is the finally hot and relatively humid air leaves the system. The entire process could be indicated on the psychrometric chart like this: 1 to 2, heating with the humidification process, in which both dry bulb temperature and as well as specific humidity of air increases. In this process, the effects could be written as dry bulb temperature increases, number 2, specific humidity increases, number 3, RH5 decreases, number 4, enthalpy of the moist air. You can see here that this is H1, this is H2. H2 is greater than H1. Number 5, WBT increases, because as the enthalpy increases, automatically wet bulb temperature also increase. Number 6, DPT, dew point temperature increases. Number 7, specific volume of the moist air also increases. Generally, this psychrometric process is employed during winter air conditioning. When the temperature of atmospheric air is low and humidities are low. Air is relatively drier during the winter conditions. That is the reason why we would have to add some moisture into the atmospheric air so that the human beings feel comfortable. The next psychrometric process what I discuss is adiabatic humidification. Adiabatic what is meant by adiabatic? Adiabatic means no heat transfer between system and surroundings. The process could be visualized like this. If we take a large sheet of water, this is all water. This water is recirculated with the help of the pump. With the help of the pump, the same water is again and again recirculated and sprayed. So it is water is falling. These are all spray washers. They can also be called as the spray washers. Onto that long sheet of water, atmospheric air is blown. So the system is called adiabatic because there is no heat transfer between the entire things. There is no heat transfer. Q is 0. That is the reason why it is called adiabatic. No heat transfer. So as the atmospheric air is passing, over a large sheet of water where same water is sprayed again and again, the air could pick up water vapor if it is unsaturated, and gets humidified. Air gets humidified. The latent heat required for the change of phase of water into vapor is provided by the air itself. Hence the temperature of air decreases, and by the time air leaves the system, the water and air attains thermal equilibrium. So writing a steady flow energy equation, or first law of thermodynamics for process, H1 is equal to H2 implies enthalpy of moist air remains constant during this process. Since H is remaining constant, WBT of moist air also remains constant because the constant wet bulb temperature lines run parallel to the constant H line is parallel to constant WBT line on psychrometric chart. Indicating adiabatic humidification process on psychrometric chart. The process is seen like this. This is state 1, state 2. dBT, temperature of the moist air decreases, humidity of the moist air increases, but the enthalpy of the moist air remaining constant. H1 is H2. So the constant enthalpy line is parallel to the constant WBT line. So 1 to 2 line is isoenthalpic as well as constant WBT line. That is the characteristic of this process. If you look at the effects of the process, number 1, dBT of moist air decreases. Number 2, WBT remains constant. Number 3, enthalpy of the moist air is constant. Number 4, dPT of the moist air increases. Number 5, specific humidity increases. Number 6, RH greatly increases because the line is cutting across the constant RH line, cutting normally to the constant RH line. RH greatly increases. Number 7, specific volume of moist air decreases. In fact, if you look at the application of this process, this process is employed In desert air coolers, where the temperature of air is very high, but the humidity of air is very low. In the desert conditions, the temperatures are very high, but the air humidity contents are very low. In such conditions, this process is applicable. That is the first application. Number 2, spray ponds. Number 3, evaporative condensers. Number 4, cooling towers. These are all the applications of this adiabatic humidification process. Coming to the next process, that is chemical dehumidification process. There are certain substances like alumina, that is aluminum oxide, or silica gel, which have affinity or attraction towards the water vapor or moisture present in air. Such materials are also called as hygroscopic materials, which can absorb the moisture or water vapor from air, from moist air. These substances, when they are exposed to the atmospheric air, they have got the affinity to absorb the water vapor from the atmospheric air. In this psychrometric process, that is chemical dehumidification process, atmospheric air is blown over this alumina or silica gel, which have got the affinity towards the water vapor. The water vapor gets condensed and the latent heat of condensation is liberated. So that heat is taken by the air itself. The air temperature increases. So the process could be seen on the psychrometric chart as so the water vapor present in atmospheric air condenses into liquid. Why? Because the water vapor has got affinity towards the alumina, and thereby liberates latent heat of condensation. The water condenses, water vapor condenses, the liberating latent heat of condensation. This heat is picked by air itself, and hence temperature of air increases. Effects of this process could be written as: number 1, dBT increases. Number 2, specific humidity W decreases. Number 3, enthalpy remains constant. Enthalpy of moist air remains constant. Number 4, WBT also remains constant. Number 5, dPT decreases, dew point temperature decreases. Number 6, RH5 also decreases. Number 7, specific volume of moist air increases. RH decreases. This is phi1, this is phi2. This process is employed in agricultural food storage applications. In fact, this is a very important thing to be noted there. Food storage applications, or the warehouse applications, this process is employed. Next, coming to the humidification process. It is the psychrometric process in which the water vapor is added into moist air at a constant temperature or isothermal conditions. Indicating the humidification process on the psychrometric chart, the process appears like this. We are increasing the humidity at constant derivable temperature, constant dBT, in which RH effects will be RH5 increases. Number 2, WBT increases. Number 3, dPT increases, but dBT constant. Enthalpy also increase. The dehumidification, it is just reverse of humidification process, in which water vapor is removed at constant dBT or isothermal conditions. Now let us indicate indication or plotting of all psychrometric processes on a single psychrometric chart. Beginning from the same state. Let us beginning from the same state. Now I want to indicate all the processes on a one single psychrometric chart beginning at a given state. Psychrometric chart x-axis is dBT, y-axis is W or specific humidity, kg of water vapor per kg of dry air. This is saturation curve. This is enthalpy scale. Enthalpy scale, that is kilojoules per kg of dry air. The first process is sensible heating, SH. SH for sensible heating, going rightwards. Second process is horizontal line, sensible cooling. The third process, cooling with dehumidification, is curve going in the leftwards down, cooling with dehumidification. Fourth process is temperature and humidity both are increasing. This is heating with humidification. Fifth process is adiabatic humidification, wherein the enthalpy remains constant. Sixth process is chemical dehumidification, wherein dPT, dew point temperature, decreases. Sixth process is humidification, isothermal humidification at constant temperature. Last process is dehumidification. So that is how we can indicate all the processes on a single psychrometric chart beginning at a given state.